Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The asteroid belt, often described as the rocky middle zone of our solar system, lies in a vast region between the orbits of Mars and Jupiter. This region is a cosmic crossroads, where countless fragments of rock and metal drift silently through space, remnants of the early solar system. Unlike planets, which formed into large, cohesive bodies, these smaller objects remained as scattered fragments, locked in a delicate gravitational dance shaped by the immense presence of Jupiter. Though it is commonly depicted as a dense, dangerous ring in popular culture, the asteroid belt is far more sparsely populated than imagined. The average distance between these rocky bodies is vast, spanning hundreds of thousands of kilometers, making actual collisions a rare event. Despite this, the belt holds the secrets of planetary formation, the history of our solar system, and even clues about the origin of life on Earth. Asteroids are the main residents of this rocky region, and they vary dramatically in size, shape, and composition. Some are small, no larger than a house, while others, like Ceres, the largest object in the belt, span hundreds of kilometers across. Ceres alone contains a significant portion of the belt's total mass, and its unique features, including evidence of water ice and possibly even past liquid water activity, make it an object of intense scientific interest. Vesta, another prominent asteroid, offers a contrasting story with its heavily cratered surface, hinting at violent collisions in its past. These varied asteroids are classified based on their composition: C-type, rich in carbon, and dark in appearance; S-type, composed mostly of silicate rock; and M-type, metallic and often brighter than their counterparts. Each type offers a window into the materials that existed in the early solar system, untouched for billions of years. The formation of the asteroid belt is a story of cosmic negotiation and gravitational influence. During the early days of the solar system, the same swirling disk of gas and dust that birthed the planets also produced countless smaller bodies. Some coalesced into planets, while others, under the strong gravitational pull of nearby Jupiter, were prevented from forming into a single planetary body. Instead, these fragments remained scattered, their orbits influenced not only by the Sun, but also by Jupiter's enormous gravitational presence. This constant tug-of-war has created a region where asteroids can follow stable orbits for millions of years, yet also a region where occasional collisions and disruptions are inevitable. The result is a dynamic environment where asteroids can collide, break apart, or even be ejected from the belt entirely. The diversity of asteroids extends beyond their composition and size to their shapes and surface features. Many asteroids are irregularly shaped, resembling lumpy potatoes more than spheres, reflecting the low gravitational forces that prevent them from rounding out like planets. Their surfaces are often scarred with craters, grooves, and ridges, evidence of impacts accumulated over eons. Some exhibit unique surface features, such as grooves on Ida, or the peculiar shape of Bennu, which has been studied extensively by spacecraft missions. These features are not just aesthetically fascinating. They provide crucial data about the mechanical properties of asteroid surfaces, their internal structures, and the history of cosmic collisions. The study of asteroids has entered a new era thanks to space missions that venture into this rocky frontier. Missions like NASA's Dawn, which visited Vesta and Ceres, and Japan's Hayabusa and Hayabusa 2, which returned samples from Itokawa and Ryugu respectively, have transformed our understanding of these seemingly simple rocks. Dawn revealed Ceres' complex geology, including evidence of cryovolcanism and the presence of briny deposits, hinting at processes once thought exclusive to larger planets. Hayabusa missions provided actual asteroid samples, allowing scientists to study their composition in laboratories on Earth. These missions not only validate theories about asteroid formation, but also open new questions about the presence of water and organic materials, linking asteroids directly to the potential origins of life. Asteroids are not merely static objects. They are also travelers capable of leaving the belt and entering the inner solar system. These wanderers, known as near-Earth asteroids, can cross paths with Earth, presenting both risks and opportunities. While some may pose collision hazards, others offer a treasure trove of resources, containing metals and water that could support future space exploration and even interplanetary colonization. The idea of asteroid mining, once purely speculative, is now under serious consideration as humanity looks toward utilizing these celestial resources to fuel a sustainable presence beyond Earth. The asteroid belt also plays a critical role in shaping the broader dynamics of the solar system. Its existence influences the orbits of neighboring planets and acts as a barrier, preventing the inner and outer planets from gravitationally interfering too dramatically with each other. The distribution of asteroids, their sizes, and their interactions reveal patterns that help astronomers understand not only our own solar system, but also the formation of exoplanetary systems around distant stars. Observations of asteroid belts and other star systems suggest that our solar system is not unique, yet it holds a distinct balance that has allowed life to flourish on Earth. Collisions within the belt, while infrequent on human timescales, have shaped its structure over billions of years. Catastrophic impacts can shatter large bodies into smaller fragments, creating families of asteroids that share similar orbits and compositions. Studying these families allows scientists to trace back their histories, identifying the original parent bodies and the events that fragmented them. In some cases, such collisions may even send fragments hurtling toward Earth, delivering vital organic compounds or triggering mass extinctions. The asteroid belt, therefore, is not merely a collection of rocks, but a dynamic and influential component of our planetary neighborhood, bridging the past, present, and future of our solar system. Despite centuries of study, many mysteries remain. The exact processes that govern the distribution of asteroids, the role of Jupiter in preventing planet formation, and the history of water and organic compounds within the belt continue to be active areas of research. Each new mission, each new observation, peels back a layer of understanding, revealing a region that is as complex as it is captivating. From the smallest pebble-sized rocks to the largest dwarf planet, the asteroid belt tells a story of creation, survival, and transformation, reflecting the delicate balance of forces that sculpted our solar system. The beauty of the asteroid belt lies not just in its physical properties, but also in its symbolic place in the cosmic narrative. It is a middle zone bridging the rocky inner planets with the gas giants beyond, a repository of ancient materials that have remained largely unchanged for billions of years. It is a laboratory, a window into the past, and a potential resource for the future. Studying this region allows humanity to trace its own origins, understand the forces that govern planetary systems, and dream of a future where humans reach out to touch and utilize these wandering rocks. Space enthusiasts and scientists alike are drawn to the asteroid belt for its combination of mystery, challenge, and potential. It is a region where the imagination can soar alongside scientific inquiry, where questions of formation, evolution, and even survival intermingle with the practicalities of space exploration. The technological achievements that have enabled missions to reach and study these distant objects highlight the progress of human ingenuity, while the discoveries themselves remind us of the vast and intricate universe we inhabit. From a scientific perspective, the asteroid belt is a bridge across disciplines. It informs planetary science, astronomy, geology, chemistry, and even astrobiology. Each rock and fragment holds clues about the early solar system's temperature, composition, and dynamics. By understanding the belt, scientists gain insight into processes that are impossible to replicate on Earth, from high-velocity collisions to the behavior of ice and rock in microgravity. The belt is a testament to the complexity and diversity of the cosmos, a microcosm of the larger universe, where gravity, chemistry, and time interact in subtle and profound ways. As humanity continues to explore space, the asteroid belt promises to remain a central focus. It is a stepping stone, a proving ground for technologies and strategies that will one day carry humans deeper into the solar system. Missions to mine asteroids, deflect potentially hazardous objects, and even establish outposts on larger bodies like Ceres may redefine our relationship with these rocky neighbors. The belt transforms from a distant, mysterious region into a tangible frontier, where knowledge, resources, and adventure converge. The story of the asteroid belt is ongoing, with each discovery prompting new questions and avenues of exploration. It challenges our understanding of planetary formation, tests our technological capabilities, and inspires visions of interplanetary travel. The belt is not simply a collection of debris, it is a living laboratory, a historical record, and a bridge to the future. Its rocks whisper the secrets of the early solar system. Its collisions remind us of the forces at play in the cosmos, and its potential resources hint at the possibilities that await humanity beyond Earth. In this sense, the asteroid belt embodies the essence of space exploration: curiosity, discovery, and the drive to reach beyond the known. It is a region where science and imagination intersect, where ancient rocks and modern technology meet, and where the mysteries of the past inform the aspirations of the future. As telescopes continue to observe, spacecraft continue to travel, and scientists continue to analyze, the belt offers endless opportunities to learn, explore, and dream. The middle zone of our solar system, often overlooked compared to the planets and moons, is a region of profound importance. The asteroid belt challenges our perceptions, revealing a landscape that is both serene and dynamic, distant yet intimately connected to the story of life on Earth. Its rocky inhabitants, from the tiniest fragment to the largest dwarf planet, form a community shaped by gravity, collisions, and time. They are relics of a bygone era, yet they hold relevance for the present and future of space exploration, planetary defense, and human ambition. Ultimately, the asteroid belt is a reminder of the complexity and beauty of our solar system. It stands as a testament to the delicate interplay of forces that have shaped planetary formation, the persistence of ancient materials over billions of years, and the potential for discovery that awaits humanity. The rocky middle zone is more than a field of asteroids. It is a bridge between worlds, a keeper of cosmic history, and a beacon for the future of exploration. As we continue to gaze upward, sending probes and imagining missions, the asteroid belt invites us to consider not just what lies beyond, but also how the smallest fragments of our solar system connect to the grand narrative of the universe. Among the most fascinating aspects of the asteroid belt is the diversity of its orbital structures. The belt is not a uniform cloud of rocks, but rather a dynamic region with complex patterns shaped by gravitational interactions. One of the most striking features are the Kirkwood Gaps, named after the astronomer Daniel Kirkwood, who first identified them in the 19th century. These gaps are regions within the belt where the gravitational influence of Jupiter destabilizes asteroid orbits, creating swaths with surprisingly few objects. The presence of these gaps demonstrates the long-lasting influence of giant planets on smaller bodies, and they serve as natural laboratories for studying orbital resonance, a phenomenon where the timing of gravitational pulls causes dramatic shifts in motion over time. Asteroids caught in these resonances may be nudged onto new paths, sometimes even ejecting them from the belt entirely, sending them into the inner solar system or out toward the distant reaches beyond Jupiter. The belt also contains families of asteroids, clusters that share similar orbits and physical characteristics, evidence of a shared origin. These families are often the result of catastrophic collisions, where a parent body was shattered into numerous fragments. By studying the composition and trajectories of family members, scientists can trace back to the original asteroid, piecing together a cosmic history written in rock. Families like the Flora, Eunomia, and Eos families reveal different compositions, from stony silicate bodies to metallic remnants, painting a picture of a belt that is as varied in its geological makeup as the planets themselves. Some of these fragments, through cosmic nudges, eventually leave the belt and become meteorites that fall to Earth, offering direct evidence of their ancient origins and serving as tangible links between our planet and the wider solar system. Meteorites themselves are a bridge between Earth and the asteroid belt. Every year, thousands of meteoroids enter Earth's atmosphere, though most burn up before reaching the surface. Occasionally, fragments survive as meteorites, and their study has revealed invaluable information about the chemical and isotopic composition of asteroids. Some meteorites, known as carbonaceous chondrites, contain organic molecules, amino acids, and even water-bearing minerals. These discoveries support the hypothesis that asteroids may have contributed to delivering the building blocks of life to Earth during its formative years, highlighting the belt's importance not just as a relic of planetary formation, but as an active participant in the history of life itself. The physical characteristics of asteroids are another window into the early solar system. Many are heavily cratered, showing a record of millennia of collisions. Others display more subtle features like grooves, ridges, and fractures, which tell scientists about their internal structures and mechanical properties. Some asteroids are rubble piles, loose conglomerations of rock held together by weak gravity, while others are more solid, monolithic bodies. The differences between these types suggest varied histories. Some may have survived relatively intact, larger bodies broken apart by catastrophic impacts. Understanding these structures is crucial for future space missions, whether the goal is exploration, resource extraction, or planetary defense. Space missions have revolutionized our understanding of the belt. NASA's Dawn mission provided an unprecedented look at two of the largest residents, Vesta and Ceres. Vesta, with its towering mountains and enormous craters, revealed a history of intense impacts and geological activity. Its crust appears differentiated, with layers indicating past heating and internal evolution. Ceres, on the other hand, surprised scientists with evidence of water ice, brine deposits, and signs of cryovolcanic activity. The discovery of bright spots within Ceres's craters, composed primarily of sodium carbonate, suggests recent geological processes and hints at the possibility of subsurface liquid reservoirs. These findings not only reshape our understanding of the belt, but also expand the scope of what is considered geologically active in the solar system. Japan's Hayabusa and Hayabusa 2 missions further pushed the boundaries by returning samples of asteroids to Earth. Hayabusa returned tiny particles from Itokawa, a small rubble pile asteroid, revealing a surface rich in silicate minerals. Hayabusa 2 brought back material from Ryugu, another carbon-rich asteroid, providing samples with organic compounds and hydrated minerals. These missions allow scientists to conduct detailed chemical and isotopic analyses impossible through remote observation, opening new doors to understanding the origins of water and organic materials in the solar system. Such studies strengthen the theory that asteroids could have played a crucial role in seeding early Earth with the ingredients necessary for life. Asteroids also present potential for future human endeavors beyond Earth. The concept of asteroid mining has transitioned from science fiction to serious consideration by space agencies and private enterprises. Many asteroids contain precious metals like platinum, gold, and nickel, while others harbor water in the form of ice, which could be converted into fuel for space missions. Establishing infrastructure to mine asteroids could provide the resources necessary for sustained human presence in space, reducing the need to launch all supplies from Earth. While such ambitions present enormous technical challenges, the scientific groundwork laid by missions to the belt brings humanity closer to transforming these rocks from passive relics into active resources. Despite the romantic notion of a belt densely packed with rocks, the reality is one of vast emptiness. The distances between individual asteroids are enormous, often hundreds of thousands of kilometers, making collisions rare in the present day. Yet when collisions do occur, they can produce spectacular events. Some impacts shatter asteroids into smaller fragments, creating debris fields that slowly evolve under the gravitational influence of the sun and planets. Others generate dust that migrates inward toward the sun or outward toward the outer solar system, forming faint rings of material. Over billions of years, these collisions have shaped the current distribution, sizes, and compositions of belt objects, maintaining a dynamic equilibrium that persists to this day. The asteroid belt's position between the inner rocky planets and the outer gas giants makes it a critical piece of the solar system's architecture. Jupiter's massive gravity serves as both a shepherd and a disruptor, shaping the belt's structure and preventing these fragments from coalescing into a planet. This interaction has implications not only for the belt itself, but also for the stability of the inner planets. Without the belt acting as a reservoir for debris and Jupiter's gravity as a stabilizing force, Earth might have faced a very different history, potentially bombarded more frequently by larger objects or experiencing destabilized planetary orbits. In this sense, the asteroid belt contributes indirectly to the conditions that allowed life to flourish on our planet. Observing asteroid belts around other stars offers a broader perspective. Astronomers have detected debris disks and asteroid-like structures in distant planetary systems, suggesting that belts like our own are common in the universe. These discoveries provide comparative laboratories for understanding planetary formation, the frequency of collisions, and the potential for water and organic delivery to planets in other systems. By studying these analogs, scientists can better understand the uniqueness and commonality of our solar system's evolution, and perhaps even assess the potential for life elsewhere. Asteroids also have cultural and philosophical significance. They are reminders of the violent, chaotic processes that shape the cosmos, of the fragility of planetary surfaces, and of the delicate balance that sustains life on Earth. They inspire literature, art, and imagination, bridging the gap between scientific discovery and human curiosity. Missions to asteroids, images of their irregular surfaces, and samples returned to Earth allow us to connect tangibly with objects billions of kilometers away, fostering a sense of connection with the wider universe. The study of asteroids continues to evolve rapidly. Advances in telescopes, spectroscopy, and space missions are uncovering ever more detailed information about their compositions, orbits, and histories. Machine learning and computational modeling allow scientists to predict asteroid collisions, orbital evolution, and potential resource locations with increasing precision. These tools, combined with direct exploration, enable a comprehensive understanding of a region once considered remote and inaccessible. Looking to the future, the asteroid belt offers both challenges and opportunities. Efforts to develop planetary defense strategies rely heavily on understanding near-Earth objects, many of which originate from the belt. Missions to deflect or mitigate potential threats will depend on detailed knowledge of asteroid composition, density, and structure. At the same time, exploration and resource utilization of the belt could support the next phase of human expansion into space, serving as a proving ground for technologies and strategies that will one day take us to Mars, the outer planets, and beyond. The asteroid belt is, in many ways, a cosmic laboratory, a historical archive, and a potential gateway to humanity's future in space. It preserves the primordial materials from which the solar system formed, provides direct insight into the processes that shape planets, and offers tangible resources for exploration. It is a region of contrasts, where serenity and violence coexist, where ancient relics drift silently alongside active geological processes, and where scientific inquiry meets human imagination. Its rocky residents, from the smallest fragments to the dwarf planets like Ceres, are not merely objects of study, but storytellers, each piece carrying a chapter of our solar system's history. They remind us of the forces that shaped Earth, the possibilities of life beyond our planet, and the potential for humanity to extend its reach into the cosmos. The asteroid belt, often overlooked in favor of planets and moons, is a cornerstone of understanding the solar system, bridging the gap between inner and outer worlds, and connecting past, present, and future. Among the most prominent residents of the asteroid belt, Ceres stands as the largest and most intriguing. With a diameter of nearly 940 kilometers, it contains roughly 40% of the belt's total mass. Ceres is classified as a dwarf planet, a distinction that sets it apart from the smaller, irregularly shaped asteroids that dominate the belt. Its surface exhibits a mix of rocky terrain and patches of water ice, suggesting that liquid water may have existed beneath its crust. The bright spots discovered within Asteroid crater, composed mainly of sodium carbonate, hint at past or even ongoing cryovolcanic activity. These reflective deposits suggest that briny water from below might have seeped to the surface in relatively recent geological times. Ceres' unique characteristics make it a prime candidate for studying the history of water in the solar system and exploring the possibility that it could have once harbored conditions suitable for life. Vesta, the second largest body in the belt, offers a contrasting narrative. Measuring about 525 kilometers in diameter, Vesta has a heavily cratered and mountainous surface, shaped by violent collisions over billions of years. Unlike Ceres, Vesta is primarily rocky and lacks significant water ice, but it provides a clear record of differentiation and internal evolution. Its surface shows layers that indicate a history of heating and cooling, revealing insights into how protoplanets in the early solar system might have formed and evolved. Dawn's close observations of Vesta's massive Rhea Silvia basin, a colossal crater nearly as wide as the asteroid itself, illustrate the sheer scale of impacts that have shaped the belt. These cataclysmic collisions not only altered Vesta's surface, but also created numerous smaller fragments, contributing to the population of smaller asteroids and meteorites in the belt and beyond. Other notable asteroids like Pallas and Hygiea add further diversity. Pallas, slightly smaller than Vesta, has an unusual orbital inclination, tilting sharply compared to most belt objects. Its high orbital tilt and irregular shape suggest a complex collisional history and potential past gravitational interactions with Jupiter. Hygiea, meanwhile, is a dark, carbon-rich asteroid that rivals Ceres in its spherical shape, highlighting the belt's compositional diversity. Its relatively uncratered surface may indicate that it has experienced fewer disruptive collisions than other large bodies, or that impacts have been erased by surface processes over time. Studying these larger bodies provides context for the smaller fragments, helping scientists reconstruct the evolutionary history of the belt and the solar system at large. Future missions promise to expand our knowledge even further. NASA's Lucy mission, launched to explore Jupiter's Trojan asteroids, will provide comparative insights that may also inform our understanding of the main belt. The Psyche mission, targeting a metallic asteroid of the same name, will explore a type of object relatively rare in the belt, but crucial for understanding planetary cores and differentiation processes. Beyond these missions, there are growing plans from both governmental and private entities to explore asteroid mining. The extraction of metals, water, and other valuable resources from asteroids could revolutionize space exploration, enabling long-term human presence in space by providing fuel, building materials, and water directly from the solar system's own resources. These missions reflect a new era where the belt is not just a subject of study, but a potential platform for humanity's future in space. Understanding the orbital dynamics of the asteroid belt is crucial for both science and practical exploration. The belt is not a simple static zone, it is a region of constant motion, influenced by the gravitational forces of the Sun, Jupiter, and to a lesser extent, Mars and Saturn. Asteroids experience orbital resonances, where repeated gravitational nudges by Jupiter create gaps or clusters within the belt. The Kirkwood gaps, for instance, are a direct result of these resonances, illustrating the delicate balance between stability and disruption. Smaller asteroids can be nudged onto new paths, sometimes leaving the belt entirely and becoming near-Earth asteroids, which may either pose collision risks or present future mining opportunities. Understanding these dynamics is critical for predicting asteroid movements, planning missions, and assessing potential hazards to Earth. Collisions remain a defining aspect of the belt's evolution. Catastrophic impacts can fragment large asteroids into smaller ones, creating families of objects with shared orbital characteristics. These collision families provide valuable insight into the past, allowing astronomers to trace fragments back to their original parent bodies. Some fragments eventually leave the belt, becoming meteoroids that may reach Earth, delivering organic compounds, minerals, and other materials essential to the story of life. The study of these collisions also informs planetary defense strategies, helping scientists predict and mitigate potential asteroid impacts on Earth. Astrobiology is another area where the asteroid belt has profound implications. The discovery of water, hydrated minerals, and organic compounds on some asteroids supports the theory that these rocky bodies could have contributed to the emergence of life on Earth. Carbonaceous chondrites, in particular, contain complex molecules, including amino acids, that may have been delivered to early Earth via impacts. This positions the belt as a critical element in the solar system's life story, a vector for prebiotic chemistry that helps set the stage for biology on our planet. Exploring asteroids for these compounds could also provide insights into whether life or its precursors might exist elsewhere in the solar system or in exoplanetary systems with similar belts. Beyond science, the asteroid belt offers practical opportunities for humanity's expansion into space. Water extracted from asteroids can be converted into hydrogen and oxygen for rocket fuel, enabling refueling stations in orbit or along interplanetary routes. Metals and other materials may support the construction of habitats, spacecraft, and other infrastructure in space, reducing reliance on Earth for resources. In this sense, the belt is both a laboratory and a supply depot, offering the materials and knowledge needed to take humanity further into the solar system. The asteroid belt's symbolic significance should not be overlooked. As a middle zone bridging the inner rocky planets and the gas giants, it represents balance and continuity in the solar system. Its rocky residents are relics of a bygone era, yet they remain active participants in the ongoing evolution of planetary dynamics. The belt embodies the interplay of stability and chaos, survival and destruction, past and future, offering a rich narrative that complements its scientific value. In conclusion, the asteroid belt is far more than a distant field of rocks. It is a dynamic, diverse, and vital component of the solar system, preserving ancient materials, recording billions of years of cosmic history, and providing resources and knowledge for the future. From Ceres and Vesta to countless smaller fragments, each asteroid tells a story of formation, collision, and survival. The belt links the inner and outer solar system, influences planetary evolution, and even hints at the origins of life on Earth. As humanity continues to explore space, the belt offers not only scientific insight, but also practical opportunities for exploration, resource utilization, and the extension of our presence into the cosmos. The rocky middle zone stands as a testament to the complexity, beauty, and potential of the universe, reminding us that even the smallest fragments can hold the greatest significance. Beyond its scientific and practical significance, the asteroid belt also holds a profound place in human imagination and culture. For centuries, people have looked to the skies and wondered about the vast spaces between planets, imagining zones filled with mysteries and treasures. The belt symbolizes the unknown frontier, a region that challenges both our understanding and our ambition. It embodies the human desire to explore, to reach beyond the familiar, and to uncover secrets that have existed for billions of years. Each asteroid, from the smallest fragment to the dwarf planets, is a silent storyteller, whispering the history of the solar system and inviting humanity to engage with the cosmos in a deeper, more personal way. Philosophically, the asteroid belt represents the concept of balance within the universe. It is a region shaped by competing forces, the stabilizing presence of Jupiter, the disruptive potential of collisions, and the subtle influence of the Sun and other planets. This delicate equilibrium mirrors the broader patterns observed throughout nature, where chaos and order coexist, and where seemingly small elements can have outsized effects. The belt's very existence illustrates the complex interplay of forces that govern not only celestial bodies, but also the conditions that made life on Earth possible. In this sense, studying the belt allows humanity to reflect on the interconnectedness of the cosmos and our place within it. Looking forward, the asteroid belt offers limitless possibilities for exploration, discovery, and even human expansion. Future missions may not only study these rocky bodies, but also harness their resources, enabling humanity to establish a sustained presence in space. Water ice, metals, and organic compounds could support life, fuel spacecraft, and construct habitats, turning the belt into a stepping stone for journeys deeper into the solar system. Moreover, advanced telescopes and robotic explorers will continue to uncover the belt's secrets, revealing new insights into planetary formation, orbital dynamics, and the potential for life elsewhere in the universe. Each new discovery will deepen our understanding, bridging the gap between imagination and reality, and reminding us that even the smallest rocks can shape the trajectory of human knowledge and ambition. The asteroid belt also inspires a sense of humility and wonder. Despite its apparent barrenness, it contains the remnants of the solar system's creation, preserved across billions of years. These fragments serve as reminders that the universe operates on scales and timespans far beyond human perception. By studying them, we are able to glimpse the processes that shape not only our planetary neighborhood, but potentially countless other star systems throughout the galaxy. The belt, in its quiet persistence, challenges us to think in terms of cosmic time, to appreciate the resilience of matter, and to recognize the intricate beauty of celestial mechanics. Ultimately, the asteroid belt is more than a physical region. It is a narrative of creation, destruction, survival, and potential. It connects the inner and outer worlds, bridges the past and the future, and links scientific discovery with human aspiration. It reminds us that exploration is not solely about reaching new destinations, but also about understanding the subtle, often overlooked elements that shape the universe. As humanity prepares to venture further into space, the belt stands as both a gateway and a guide, offering lessons in resilience, adaptation, and the endless possibilities that await among the stars. In contemplating the asteroid belt, we are invited to consider our place in the cosmos, the forces that shaped our world, and the future we may carve among the stars. Each asteroid, each collision, each fragment of rock is a chapter in a vast, ongoing story that spans billions of years. By studying and exploring this rocky middle zone, humanity not only uncovers the secrets of the solar system, but also glimpses the potential for its own future, stretching beyond Earth to participate actively in the cosmic journey. The asteroid belt, silent yet profound, continues to challenge, inspire, and guide us, proving that even in the seemingly empty spaces of the universe, there lies infinite knowledge, opportunity, and wonder.